13.8 billion years ago, everything that ever was or ever will be exploded into existence from a point smaller than the period at the end of this sentence. But here's what will blow your mind. We're about to journey into the impossible realm before that moment, where nothing wasn't empty space, where time didn't tick, and where the very concept of existence breaks down completely. We'll explore quantum foam bubbling with virtual particles, infinite multiverses colliding, and mathematical realities that make our universe look tiny. If you're ready to question everything you think you know about reality, hit that like button and subscribe. Prepare yourselves, we begin. Picture the ultimate deadline, the literal end of before and the birth of when. Scientists call it T0, but that innocent label hides the most violent transformation in cosmic history. At this boundary, the very concept of before becomes meaningless because time itself didn't exist yet. Think about that for a second. No ticking clocks, no aging, no sequence of events. Not darkness waiting for light, but the complete absence of duration itself. The mathematics break down here like a computer dividing by zero. Einstein's equations, which describe gravity and spacetime with perfect precision everywhere else, simply stop working. They produce infinities and impossible answers. It's as if the universe has a "do not enter" sign written in the language of physics itself. But here's where it gets truly strange. The moment we're trying to understand isn't just the beginning of our universe. It's the beginning of the very framework that lets beginnings happen. Before this instant, there was no stage for any cosmic drama to unfold on. No dimensions to measure, no space to fill, no time to pass. Imagine trying to describe the color of something that has never reflected light, in a place where light itself is impossible. That's what we're attempting when we ask what came before the Big Bang. We're using concepts that only make sense after the moment we're trying to examine. Yet modern physics suggests something profound was happening in this impossible realm. Quantum mechanics tells us that even in perfect emptiness, energy can briefly flicker into existence and vanish again. These quantum fluctuations happen constantly in the vacuum of space today. But if they could happen in absolute nothingness, then perhaps nothing was never truly nothing at all. The leading theory suggests our entire universe began as one of these quantum fluctuations, but instead of disappearing, it grew in less than a trillionth of a trillionth of a trillionth of a second. This microscopic bubble of energy expanded faster than light itself, creating space as it went. Think of it like a soap bubble forming on the surface of completely still water, except the water doesn't exist, the surface doesn't exist, and somehow the bubble creates both as it grows. The bubble becomes the entire pond, the entire world, the entire everything. This process, called cosmic inflation, explains why our universe looks so uniform in every direction. It also explains why space appears flat instead of curved. But it raises an even more mind-bending question physicists are still wrestling with today. If quantum fluctuations can create one universe from nothing, why would they stop there? The mathematics suggest they wouldn't. They suggest something far more extraordinary than a single cosmic beginning. But what we discover next makes our origin story look simple. When you empty a jar completely, is it really empty? Most people would say yes, but physics reveals something shocking. What we call empty space is actually buzzing with invisible activity. Even in the deepest vacuum between galaxies, where matter is so sparse you might find one atom per cubic meter, space itself remains alive with energy. This isn't the kind of nothing philosophers debate about. This is measurable, detectable, experimentally proven nothingness that refuses to stay nothing. Scientists discovered this when they tried to cool things down to absolute zero and remove every last bit of energy from a system. They found something impossible. The energy never reaches zero. Even at the coldest possible temperature, 460 degrees F, quantum fields still vibrate with what physicists call zero-point energy. It's like trying to calm a pot of boiling water, but no matter how much heat you remove, tiny bubbles keep forming and popping at the bottom. These quantum fields fill every cubic inch of space, creating what scientists call the quantum vacuum. Picture an ocean that looks perfectly calm on the surface, but beneath the waves, countless creatures swim in patterns too quick and small for your eyes to catch. The quantum vacuum works the same way, appearing empty, while hosting constant creation and destruction at scales smaller than atoms. Here's where it gets weird. These quantum fields can borrow energy from the future to create pairs of particles that pop into existence, dance briefly together, then annihilate and disappear. This happens trillions of times per second, in every tiny volume of space around you right now. The borrowed energy gets paid back so quickly that the universe's accounting system never notices the debt. Scientists prove this isn't just theory by measuring the Casimir effect. When you place two metal plates extremely close together in a vacuum, the quantum fields between them have less room to fluctuate than the fields outside. This creates a tiny but measurable force pushing the plates together. Empty space literally exerts pressure. But here's what will make your head spin. If our observable universe came from quantum fluctuations in a vacuum, what was that vacuum sitting in? What provided the quantum fields that could fluctuate in the first place? We're forced to ask whether even deeper layers of nothingness exist. Some physicists propose that mathematics itself might be the foundation beneath everything. Not numbers written on paper, but pure mathematical relationships that exist independently of physical reality. In this view, our universe isn't made of matter and energy, but of mathematical patterns complex enough to experience themselves. Others suggest that consciousness plays a fundamental role in creating reality through observation. Quantum mechanics shows us that particles exist in multiple states simultaneously until something measures them. Could the act of observation by conscious beings actually collapse infinite possibilities into the single reality we experience? These questions push us toward an even stranger possibility about what existed before existence. Right now, particles are appearing and disappearing inside your body. These aren't science fiction special effects. They're virtual particles, and they're fundamental to how reality works at its deepest level. Every second, quadrillions of these ghostly entities flicker into existence throughout your cells, live for impossible fractions of time, then vanish without a trace. Virtual particles sound like make-believe, but they produce real measurable effects. They're responsible for the magnetic properties of electrons, the way light interacts with matter, and even the force that keeps atomic nuclei from flying apart. Without virtual particles, atoms couldn't exist, chemistry would be impossible, and you wouldn't be here. Think of virtual particles like cosmic credit cards. They borrow energy from the quantum vacuum, spend it briefly on existing, then pay it back by disappearing. The shorter their lifetime, the more energy they can borrow. Some virtual particles live for only 10 to the 24th seconds, but during that incomprehensibly brief moment, they can carry enormous amounts of energy. The quantum vacuum isn't empty space waiting to be filled. It's more like a cosmic soup where ingredients constantly dissolve and reform. Virtual photons carry electromagnetic forces between charged particles. Virtual gluons bind quarks together inside protons and neutrons. Virtual particles of every type pop in and out of existence, creating an invisible foundation beneath visible reality. Here's the mind-bending part. These virtual particles can sometimes become real. When enough energy gets pumped into the quantum vacuum, virtual particle pairs can separate before they annihilate each other, becoming permanent additions to reality. This happens around black holes, where intense gravitational fields provide the energy needed for virtual particles to escape their quantum debt. Stephen Hawking discovered that black holes actually evaporate by turning virtual particles real. Near the event horizon, virtual particle pairs get separated by gravity. One particle falls into the black hole, while its partner escapes into space as real radiation. The black hole loses energy in this process, slowly shrinking until it completely disappears in a final burst of light. This process suggests something profound about the nature of existence. If virtual particles can become real when given enough energy, and if our entire universe might have started as a quantum fluctuation, then the boundary between real and virtual becomes surprisingly thin. Some physicists propose that our whole universe might still be virtual in some sense, borrowing its energy from an even deeper level of reality that we haven't discovered yet. In this view, everything we call real, from planets to people to galaxies, exists on borrowed time in a cosmic quantum fluctuation that started 13.8 billion years ago. But if virtual particles can create our universe, they might be creating others too. The same quantum vacuum that spawns fleeting virtual particles around us might be spawning entire cosmos in realms we can't detect. The implications of this realization lead us to a possibility that dwarfs even our cosmic beginning. Our universe might be one bubble in an infinite cosmic bath. Right now, as you read these words, countless other versions of you might be reading slightly different versions of this sentence in parallel universes. Some of those universes are nearly identical to ours, differing only in the position of a single electron. Others are so strange that the laws of physics work completely differently. The multiverse theory emerged when physicists realized that quantum fluctuations don't have to stop with creating one universe. If the quantum vacuum could produce our cosmos, it could produce others. In fact, the mathematics suggest it must produce others, constantly and endlessly, like soap bubbles forming on the surface of an infinite sea. Each universe would begin with its own Big Bang, expand through its own version of cosmic inflation, and develop its own unique properties. Some might have stronger gravity, making stars burn faster and die younger. Others might have weaker electromagnetic forces, preventing atoms from forming at all. Most would be sterile wastelands where complexity never develops, but a few might harbor forms of life we can't imagine. Picture an eternal cosmic ocean where every possible wave eventually forms. Our universe is just one wave in this ocean, temporary and unique, but not special. The multiverse doesn't care about our existence any more than the ocean cares about individual drops of water. But here's where it gets truly staggering. Some versions of multiverse theory suggest there are infinite universes, which means every possible variation of reality exists somewhere. There's a universe where dinosaurs never went extinct. There's a universe where gravity repels instead of attracts. There's a universe where you decided to become an astronaut instead of reading this script. These parallel realities aren't science fiction fantasies. They emerge naturally from our best mathematical descriptions of quantum mechanics and cosmic inflation. When you solve the equations that govern the quantum vacuum, infinite universe creation falls out as an inevitable consequence. The implications are breathtaking and terrifying. If infinite universes exist, then every possible tragedy and triumph is happening somewhere right now. Every book that could be written already exists in some universe. Every scientific discovery that could be made has already been made in countless parallel realities. Some physicists push this idea even further, suggesting that the multiverse itself might be just one level in an even grander hierarchy. Perhaps there are infinite multiverses, each containing infinite universes, stacked in layers of reality that stretch beyond our ability to comprehend. But if parallel universes exist, they might not stay parallel forever. Quantum mechanics suggests that universes could collide, merge, or influence each other in ways we're just beginning to understand. The cosmic microwave background radiation that fills our sky might contain subtle signatures of collisions with other universes that happened billions of years ago. This possibility points toward an even more radical idea about what existed before our beginning. What if our Big Bang wasn't the beginning, but the latest restart? Imagine a cosmic phoenix that dies in flames every trillion years only to be reborn from its own ashes. Some physicists propose that our universe follows this pattern, cycling through endless rounds of expansion, collapse, and rebirth. In this view, the Big Bang wasn't creation from nothing, but transformation from something that came before. The cyclic universe model suggests that our cosmos expands for billions of years, just as we observe today. But eventually, the expansion slows, stops, and reverses. Gravity wins the ultimate battle, pulling every galaxy, every star, every atom back together in a cosmic collapse called the Big Crunch. But here's the twist. Instead of ending in complete destruction, the Big Crunch becomes a Big Bang. The universe bounces back from maximum compression, erupting into a new cycle of expansion. Time doesn't end during this transition. It continues through what physicists call a cosmic bounce. Think of it like a cosmic trampoline. Our universe falls toward the trampoline's surface, accelerating as it approaches maximum density. Then the trampoline's elasticity kicks in, launching the universe back up into a new cycle of expansion. Each bounce creates what looks like a Big Bang from the inside, even though it's really just another oscillation in an eternal rhythm. This model solves several puzzles that plague traditional Big Bang theory. It explains why our universe appears so uniform in temperature and density, without requiring the incredibly rapid inflation that standard models demand. It also eliminates the uncomfortable question of what caused the Big Bang, because there was no ultimate beginning, just endless cycles. Recent observations of our universe's accelerating expansion, driven by mysterious dark energy, seem to rule out a future Big Crunch, but cyclic theorists have adapted their models to include dark energy. They propose that dark energy strength changes over cosmic timescales, eventually veering from expansion driving to contraction driving. In some versions of cyclic cosmology, each cycle lasts about 1 trillion years. Our current cycle began 13.8 billion years ago, making us relatively young in cosmic terms. We have hundreds of billions of years left before the expansion stops and collapse begins. But each cycle might not be identical. Small variations could accumulate over cosmic generations, making each universe slightly different from its predecessor. Perhaps consciousness and intelligence evolve further in each cycle, as information somehow carries over from one cosmic generation to the next. Other cyclic models propose that parallel universes take turns expanding and contracting like cosmic pistons in an infinite engine. While our universe expands, others contract. While others explode into new Big Bangs, we coast through our expansion phase. These ideas suggest that the question, what came before the Big Bang, has a simple answer: the previous cycle. But this just pushes the mystery deeper. What started the endless cycling in the first place, and could the cycles ever end? Reality might have 6 invisible dimensions wrapped around every point in space. Right now, as you sit reading this, you're surrounded by dimensions you can't see, touch, or directly experience. According to string theory, these hidden dimensions are curled up so tightly that they exist at every location in our familiar 3-dimensional world, but at scales so small that even our most powerful microscopes can't detect them. Think of a garden hose seen from far away. It looks one-dimensional like a line, but zoom in close, and you discover it has hidden circular dimensions wrapped around its length. String theory suggests our universe works the same way. What we experience as 3 dimensions of space, plus 1 of time, might actually be 4 dimensions unfolded from a reality that contains 10 or 11 total dimensions. These extra dimensions aren't empty space. They're dynamic, shape-shifting arenas where the fundamental forces of nature play out. The strength of gravity, electromagnetism, and nuclear forces in our familiar dimensions depends on how the hidden dimensions are curved and twisted. In string theory, the smallest building blocks of reality aren't particles, but tiny vibrating loops of energy called strings. These strings are unimaginably small, about 10^3 long. That's so tiny that if you scaled an atom up to the size of our solar system, a string would still be smaller than a tree. Each different vibration pattern of these strings creates what we perceive as different particles. An electron is a string vibrating one way. A photon is the same string vibrating differently. A quark is another vibration pattern. It's like a cosmic symphony where every note is a different fundamental particle. But here's where it connects to our cosmic origins. String theory suggests that the Big Bang might have been triggered by collisions between higher dimensional objects called brains. Our entire universe could be a 3-dimensional membrane floating in higher dimensional space, like a soap film on the surface of a multi-dimensional bubble. When 2 brains collide in this higher dimensional realm, the impact releases enormous amounts of energy into each brain. From our perspective inside one of these brains, this energy release looks like a Big Bang. Time and space, as we know them, begin at the moment of collision, but the brains themselves existed before the crash. This brain collision model explains several mysteries about our universe's beginning. It accounts for the incredible uniformity of the cosmic microwave background radiation without requiring faster-than-light inflation. It also suggests that what we call the Big Bang was actually a transition from one state of the brain to another, not creation from absolute nothingness. The hidden dimensions might even contain parallel brains hosting other universes. These parallel realities could be as close as a millimeter away from us in higher dimensional space, but completely unreachable because we're trapped on our 3-dimensional brain. This leads to an even more mind-bending possibility about the nature of cosmic creation. Somewhere in the cosmos, new universes are being born every second. While you've been reading the script, countless Big Bangs have erupted in distant regions of space, each one creating an entire cosmos filled with billions of galaxies. This isn't science fiction. It's the logical consequence of eternal inflation theory, one of the most successful models in modern cosmology. Traditional inflation theory explains how our universe grew from subatomic to cosmic size in its first fraction of a second, but eternal inflation suggests that this process never actually stops. It just moves from place to place, creating an endless sequence of pocket universes in an ever-expanding multiverse. Picture a pot of boiling water where bubbles constantly form and separate from the surface. Each bubble represents a universe like ours, with its own space, time, and physical laws. The boiling water represents the inflating field that fills the multiverse, forever creating new bubbles of reality. Our observable universe is just the inside of one such bubble. The Big Bang wasn't the beginning of everything, but the moment when our local region of space stopped inflating and began the slower expansion we observe today. But outside our bubble, the cosmic inflation field continues its exponential growth, occasionally spawning new pocket universes. This process has no beginning and no end. Even if inflation started at some point in the past, once it begins, it produces infinite future time and infinite space. The multiverse grows so fast that no matter how many pocket universes form, there's always room for infinitely more. Each pocket universe could have different physical constants. In some, gravity might be stronger, making stars burn out quickly. In others, the electromagnetic force might be weaker, preventing complex chemistry. Most pocket universes would be sterile, but occasionally one would have the right conditions for complexity and life. The distances between pocket universes are staggering beyond imagination. They're separated by regions of still inflating space that grow faster than light can cross them. Even if you could travel at light speed forever, you would never reach another pocket universe, because the space between you and it expands faster than you can cross it. But here's the truly mind-bending part. In an eternally inflating multiverse, every possible universe exists somewhere. There's a pocket universe where the laws of physics allow faster than light travel. There's another where time runs backwards. There's even one where the constants are tuned so precisely that black holes naturally evolve into conscious beings. This infinite proliferation of realities raises profound questions about the nature of existence itself. If every possible universe exists, then possibility and actuality become the same thing. Everything that can happen does happen somewhere in the eternal multiverse. Some physicists worry that eternal inflation makes science impossible by predicting that anything can happen somewhere. Others embrace it as the most elegant explanation for why our universe seems so perfectly tuned for complexity and life. But even eternal inflation leaves a deeper mystery unsolved. At the edge of the Big Bang, mathematics itself breaks down. Physicists have traced our universe's history back to within a tiny fraction of a second after the Big Bang began. They can describe the formation of the first atomic nuclei, the birth of the first stars, even the moment when space became transparent to light. But there's one boundary they cannot cross, one moment when all their equations produce nonsense. This boundary is called the Planck epoch. Lasting from time 0 to about 10.3 seconds after the Big Bang, during this incomprehensibly brief interval, the universe was so hot and dense that quantum effects dominated gravity itself. Space and time became grainy and uncertain, like a photograph enlarged until you can see the individual pixels. At the Planck scale, the smooth fabric of spacetime that Einstein described gets shredded into quantum foam. Distances smaller than the Planck length, about 10.3 m, become meaningless. Time intervals shorter than the Planck time, about 10.3 seconds, cannot be measured even in principle. Think of trying to use a ruler made of atoms to measure something smaller than an atom. The ruler itself becomes the limiting factor. Similarly, when we try to probe the Planck epoch, our concepts of space and time become the limitation. We're trying to use spacetime to understand the origin of spacetime itself. This creates what physicists call the boundary problem. Every equation in physics assumes that space and time exist as a background stage where events can unfold. But at the moment of the Big Bang, there was no stage. The stage itself was being created along with the very concepts of moment and creation. Einstein's general relativity, our best theory of gravity and spacetime, predicts that all matter was compressed into a mathematical point of infinite density called a singularity. But infinities in physics usually signal that a theory has reached its limits. Reality doesn't actually contain infinities. Our mathematical descriptions just break down. Quantum mechanics suggests that the singularity should be replaced by something else, perhaps a region of maximum possible density, where space and time become quantized like energy levels in an atom. But we don't yet have a complete theory of quantum gravity to describe this realm. Some physicists propose that asking what happened before the Planck epoch is like asking what's north of the North Pole. Time itself might have a boundary, a first moment that wasn't preceded by anything. In this view, the Big Bang represents the absolute beginning of temporal existence. Others suggest that time might be emergent, arising from more fundamental timeless processes. Just as temperature emerges from the motion of countless atoms, time might emerge from quantum interactions in a deeper reality that doesn't experience duration. This boundary problem points toward one of the deepest mysteries in all of science. the relationship between information and existence itself. Before the universe began, where was the information needed to create it? Every particle in your body, every atom in every star, every quantum state in every galaxy contains information. Your DNA carries information about your biological structure. The quantum states of electrons in your brain carry information about your thoughts and memories. The universe is fundamentally made of information, but where did all this information come from originally? Think about a simple hydrogen atom, the most basic element in the cosmos. Even this seemingly simple system contains precise information about the electron's energy level, spin direction, and orbital characteristics. Multiply this by every atom in every galaxy, and the amount of information in our observable universe becomes astronomical beyond comprehension. Traditional physics treats information as something that gets encoded into matter and energy that already exist, but quantum mechanics reveals something strange. Information itself might be more fundamental than the matter and energy that carry it. In quantum systems, the information about a particle's state determines what the particle is, not the other way around. This leads to a paradox that cuts to the heart of cosmic origins. If our universe began from quantum fluctuations in empty space, where did the information content of those fluctuations come from? Empty space shouldn't contain the vast libraries of information needed to specify the properties of billions of galaxies. Some physicists propose that information is conserved like energy, meaning it can never be created or destroyed, only transformed. In this view, the information in our universe must have existed before the Big Bang in some form. But this just pushes the mystery back another level. What stored all that information before space and time existed? The holographic principle offers a mind-bending solution. It suggests that all the information in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region, like a hologram that contains a complete three-dimensional image on a flat surface. Applied to cosmology, this means all the information in our universe might be encoded on its boundary at the cosmic horizon. From this perspective, our three-dimensional reality might be a projection of information stored on a distant two-dimensional surface. We could be living inside a cosmic hologram without knowing it. But this still doesn't explain where the boundary information came from originally. Some theorists propose that information is truly fundamental, existing independently of space, time, matter, and energy. In this view, physical reality emerges from pure information processing, like a cosmic computer running the program we call the universe. If information is fundamental, then asking where it came from might be like asking why mathematics works. The information simply exists as a basic feature of reality, needing no further explanation. Our universe would be one possible arrangement of this primordial information, selected by processes we don't yet understand. This information-first view of reality points toward an even stranger possibility about the nature of existence itself. True nothingness might be impossible. Imagine perfect emptiness. No matter, no energy, no space, no time, no fields, no forces, no possibilities for anything to happen. This is what most people think of as absolute nothingness. But quantum mechanics suggests that such a state cannot exist even in principle. The reason lies in the uncertainty principle, one of the fundamental laws governing reality at its smallest scales. This principle states that you cannot know both the exact position and exact momentum of any particle simultaneously, but it applies to more than just particles. It also applies to energy and time, and to the quantum fields that fill all of space. In a perfectly empty region with zero energy, you would know the energy exactly, but the uncertainty principle forbids this perfect knowledge. Therefore, the energy must fluctuate, borrowing from and paying back to the quantum vacuum in a cosmic shell game that never stops. These fluctuations aren't just mathematical artifacts, they produce real observable effects. Virtual particles pop into existence, exist briefly, then annihilate each other and disappear. The stronger the fluctuation, the shorter its lifetime. But during that brief moment, borrowed energy can create temporary realities. Now here's the staggering part. If quantum fluctuations can happen in empty space, they should also be able to happen in the absence of space itself. Pure nothingness, if it could exist, would still be subject to quantum uncertainty. This means that nothingness would fluctuate, creating something from nothing through the fundamental laws of quantum mechanics. These fluctuations in pure nothingness wouldn't be limited to tiny particle pairs. The uncertainty principle allows for enormous fluctuations if they last for incredibly short times. A fluctuation large enough to create an entire universe would be allowed as long as it pays back its borrowed energy quickly enough. But here's where cosmic inflation enters the picture. If the universal fluctuation inflated rapidly enough, it could grow larger than its own quantum wavelength before the payback time expired. Once this happens, the fluctuation becomes real and permanent, transforming from borrowed existence into actual existence. Think of it like a quantum credit card with no spending limit, but immediate payment requirements. Most purchases get reversed instantly, but occasionally a purchase grows so large that it escapes the system's ability to reverse it. The debt becomes real, but so does the purchase. Our entire universe might be the result of such a quantum fluctuation that grew too big to be reversed. From this perspective, existence itself is a kind of cosmic accident, a quantum hiccup that inflated beyond the point of no return. But if one universe can fluctuate into existence from pure nothingness, others should be fluctuating into existence constantly. Pure nothingness, if it ever existed, would be inherently unstable, spawning endless realities through quantum uncertainty. This raises a profound question. If nothingness is impossible, has something always existed? The answer leads us to consider the role of consciousness itself. What if the universe needs observers to exist? Quantum mechanics presents us with a puzzle that has haunted physicists for nearly a century. Before measurement, particles exist in multiple states simultaneously, spread out in clouds of possibility. But the moment someone observes them, these possibilities collapse into definite realities. The act of observation literally creates the reality being observed. This isn't philosophy, it's experimentally verified science. Electrons can be in multiple places at once until detected. Photons can travel through multiple paths simultaneously until measured. The quantum world remains fundamentally uncertain until consciousness looks at it. But here's the mind-bending question. If observation creates reality, what observed the universe before conscious beings evolved? How could the universe exist for billions of years before the first minds appeared to collapse its quantum possibilities into definite states? Some physicists proposed that consciousness itself might be fundamental to the cosmos, not something that emerged from complex arrangements of matter, but something that was present from the very beginning. In this view, the Big Bang wasn't just the creation of matter and energy, but the first moment when cosmic consciousness began observing itself. Think of reality as a vast quantum computation, with consciousness as the processor that turns possibilities into actualities. Without consciousness to run the program, the universe would remain a cloud of unrealized potential, forever suspended in quantum superposition. This idea suggests that what existed before the Big Bang was pure consciousness, without content, infinite potential awareness, with nothing yet to be aware of. The Big Bang would represent the moment when consciousness began to observe itself, creating space, time, and matter through the act of self-observation. But if consciousness creates reality through observation, then different types of consciousness might create different types of reality. Human consciousness, with its particular patterns of attention and measurement, shapes the universe in ways that reflect our cognitive structures. Alien consciousness, with different sensory systems and mental patterns, might observe a fundamentally different universe into existence. This raises extraordinary possibilities about parallel realities. Every conscious decision you make might split the universe, creating branches where different choices play out. Every observation you make might select one reality from countless quantum possibilities. Your consciousness doesn't just observe the universe, it participates in creating it moment by moment. Some interpretations of quantum mechanics suggest that all possible realities exist simultaneously in a vast multiverse, but consciousness selects which branch it experiences. From this perspective, before the Big Bang, all possible universes existed as pure potential. The emergence of consciousness created the first definite reality by selecting one possibility from the infinite quantum menu. If consciousness is fundamental rather than emergent, then it might be the one thing that doesn't need to be created or explained. It simply is, like existence itself. The universe might be consciousness exploring its own infinite potential through the experience of space, time, and matter. This leads us to an even more radical possibility about the relationship between mind and mathematics. What if reality is literally made of mathematics? Right now, you might think you're reading words made of matter, sitting in a physical chair, breathing real air. But according to the mathematical universe hypothesis, you're actually experiencing mathematical structures so complex they've become self-aware. You aren't made of atoms and molecules. You're made of numbers and equations that have learned to think. This isn't metaphor or analogy. MIT physicist Max Tegmark seriously proposes that mathematical existence and physical existence are identical. Every electron, every photon, every quantum field is actually a mathematical object. The universe doesn't just follow mathematical laws, it is mathematics. Think about what mathematics really represents. When you use algebra to describe motion, you're not creating an approximation of reality, you're discovering the actual structure of reality itself. The equations don't describe something else, they are the something else. Physical objects are mathematical objects that have achieved sufficient complexity to interact with themselves. This idea solves a puzzle that has bothered scientists for centuries. Why is mathematics so unreasonably effective at describing the natural world? The answer is simple. Mathematics works perfectly because reality is mathematics. We're not discovering mathematical approximations to physical laws. We're discovering the mathematical structures that constitute existence itself. But here's where it gets truly mind-bending. If our universe is a mathematical structure, then every possible mathematical structure should also exist as a physical universe. There's a universe based on different geometries where space has 4 dimensions instead of 3. There's a universe where the mathematical constants have different values, making physics work differently. Every mathematical theorem, every possible equation, every conceivable logical system corresponds to an actual universe somewhere in the ensemble of all mathematical reality. Our universe happens to be described by the particular mathematics we observe, but countless other universes are described by different mathematics. From this perspective, the Big Bang wasn't the creation of matter and energy from nothing. It was the moment when a particular mathematical structure became complex enough to support observer moments, conscious experiences embedded within the mathematical framework. You're not a biological creature observing a mathematical universe. You're a mathematical pattern that has achieved self-awareness. This explains what existed before the Big Bang. Mathematics itself existed in all its infinite complexity and possibility. The ensemble of all mathematical structures was complete and eternal, containing every possible universe as a subset. Our Big Bang represents the moment when observers first appeared within one particular mathematical structure. Time itself becomes an illusion in this view. The mathematical structures that constitute reality exist timelessly, like geometric theorems. We experience time because we're embedded within structures that contain temporal sequences, but from outside the structure, all moments exist simultaneously. The mathematical universe hypothesis suggests that consciousness isn't something separate from mathematics, but rather what complex mathematics feels like from the inside. When mathematical structures become sufficiently intricate and self-referential, they generate subjective experience. This leads us to confront one of the deepest mysteries in all of cosmology: dark energy. Dark energy shouldn't exist, but it's tearing our universe apart. In 1998, astronomers made a discovery that shattered everything physicists thought they knew about cosmic destiny. Instead of slowing down due to gravity, the expansion of the universe was speeding up. Something was pushing galaxies apart with ever-increasing force, and nobody had any idea what it was. They called this mysterious force dark energy, and it makes up about 70% of everything that exists. Dark energy is invisible, undetectable except through its effects on cosmic expansion, and it completely defies our understanding of how energy should behave. Normal energy gets diluted as space expands, like perfume spreading through a room. Dark energy gets stronger. The leading explanation involves the cosmological constant, a number Einstein added to his equations to keep the universe static. He later called it his greatest blunder when observations showed the universe was expanding. But the recent discovery of accelerating expansion suggests Einstein's blunder was actually a profound insight into the nature of reality. The cosmological constant represents the energy density of empty space itself. Even perfect vacuum contains energy, and this vacuum energy creates a repulsive force that pushes space apart. It's like the universe is filled with an invisible substance that makes space itself want to expand. But here's the problem that keeps physicists awake at night. When you calculate how much vacuum energy empty space should contain using quantum mechanics, you get a number that's 10,120 times larger than what we observe. That's not a small error, it's the worst prediction in the history of science. If quantum mechanics is right about vacuum energy, our universe should be expanding so fast that atoms couldn't form, stars couldn't shine, and galaxies couldn't exist. The fact that we're here to ask these questions means that somehow the universe has tuned its vacuum energy to a value incredibly close to zero, but not exactly zero. This fine-tuning is so precise it seems impossible to have happened by chance. It's like balancing a pencil on its point for billions of years while earthquakes shake the table. Yet somehow the universe has achieved this impossible balance. Some physicists propose that what we call dark energy isn't vacuum energy at all, but some other field that mimics the cosmological constants effects. Others suggest that the laws of physics themselves might evolve over cosmic time, with the cosmological constant changing as the universe ages. The multiverse offers another explanation. If infinite universes exist with different vacuum energies, most would expand too fast or collapse too quickly for complexity to develop. We observe a universe with the right cosmological constant because we couldn't exist in universes with the wrong value. But this raises an even deeper mystery. Why do the fundamental constants of nature seem perfectly tuned for the existence of complexity, consciousness, and life? The answer might reveal the deepest secret about what came before our cosmic beginning. The force destroying our universe might be left over from its creation. Dark energy remains the greatest mystery in modern physics, but its origin story might be written in the first moments after the Big Bang. Some physicists propose that dark energy is actually fossil energy from cosmic inflation, the rapid expansion that stretched our universe from subatomic to cosmic size in its first fraction of a second. During inflation, space itself expanded faster than light, driven by a quantum field called the inflaton. This field contained enormous energy density, enough to create all the matter and energy we see today when inflation finally ended. But what if inflation never completely ended? What if a tiny remnant of the inflaton field still permeates space? This remnant wouldn't be strong enough to drive rapid inflation like in the early universe, but it could provide the gentle push that's accelerating cosmic expansion today. Dark energy might be the dying breath of the force that created our universe, still echoing through space after nearly 14 billion years. Think of it like the ripples from a stone thrown into a perfectly still pond. Long after the stone has sunk and the initial splash has subsided, tiny ripples continue spreading outward. Dark energy could be the final ripple from the cosmic inflation that birthed our universe. But here's where it gets stranger. If dark energy comes from leftover inflation energy, then it should be slowly decreasing as the universe expands. Eventually, it should fade away completely, allowing gravity to slow cosmic expansion once again. Our current phase of acceleration would be temporary, a transitional period between the matter-dominated past and an unknown future. Other theories suggest dark energy might be increasing instead of decreasing. If this is true, cosmic expansion will accelerate faster and faster until it tears apart galaxies, solar systems, atoms, and even space itself. This scenario, called the Big Rip, would end our universe in about 22 billion years, when expansion becomes so violent that the fabric of spacetime itself gets shredded. Alternatively, dark energy might oscillate, sometimes pushing expansion and sometimes resisting it. This could create cycles of acceleration and deceleration, perhaps even leading to future periods of cosmic contraction and new Big Bang events. The most disturbing possibility is that dark energy represents a fundamental instability in the quantum vacuum itself. Our current vacuum state might be a false vacuum, temporarily stable, but destined to decay into a lower energy state. When this happens, a bubble of true vacuum will expand at light speed, destroying everything in its path and rewriting the laws of physics. This vacuum decay could have already begun somewhere in the observable universe. The destruction bubble would be invisible until it arrives, traveling at light speed and erasing reality as it expands. We would never see it coming. Dark energy forces us to confront the possibility that our universe's apparent stability is an illusion, a temporary calm before an inevitable storm that will reshape or destroy everything we know. The universe seems designed for our existence, and nobody knows why. Right now, you exist because of the most incredible cosmic coincidence in all of science. The forces that govern reality are balanced so precisely that changing any one of them by even a tiny amount would make stars impossible, atoms unstable, or complexity of any kind completely forbidden. Consider gravity the weakest fundamental force. If gravity were just slightly stronger, stars would burn through their fuel in millions of years instead of billions, never giving life time to evolve. If gravity were slightly weaker, stars would never form at all because gas clouds couldn't collapse under their own weight. The electromagnetic force shows the same impossible precision. Make it a little stronger, and electrons would bind so tightly to atomic nuclei that chemistry would be impossible. Make it weaker and atoms would fall apart, making molecules and complex structures forbidden by physics itself. The strong nuclear force that holds atomic nuclei together is tuned even more precisely. Change it by just 5% in either direction, and you eliminate either carbon or oxygen from the universe. Without both elements, the chemistry of life becomes impossible. But the most shocking example involves the cosmological constant that drives dark energy. As we discussed earlier, quantum mechanics predicts this constant should be 10,120 times larger than observed. Yet somehow, it's tuned to almost exactly zero, allowing the universe to exist for billions of years, instead of expanding so fast that matter can never clump together. The odds of all these constants randomly falling within the narrow ranges that allow complexity are essentially zero. It's like throwing a dart from 1,000,000 miles away and hitting a target the size of a single atom. The probability is so small that it might as well be impossible. This fine-tuning problem forces us to ask uncomfortable questions about the nature of reality. Did someone or something set these constants deliberately? Are we living in a designed universe crafted specifically to allow consciousness and complexity to emerge? Most physicists reject the idea of intelligent design, but they're left with equally mind-bending alternatives. The multiverse hypothesis suggests that infinite universes exist with random physical constants. Most are sterile wastelands, but we observe a fine-tuned universe because we couldn't exist in any other type. The anthropic principle pushes this idea further, suggesting that the universe must be compatible with consciousness because conscious observers are here to study it. We don't observe random physical constants because random constants usually don't produce observers. But some physicists propose that consciousness itself might play a role in selecting the physical constants through quantum measurement effects. If observer moments help collapse quantum possibilities into definite realities, then the act of observation might literally tune the universe to be compatible with observers. This leads to the most radical possibility of all, that consciousness and physical reality co-evolve together, each shaping the other in ways we're only beginning to understand. Other universes might be crashing into ours right now. While you read these words, our universe could be colliding with parallel realities in slow motion, leaving subtle fingerprints across the cosmic sky. These collisions wouldn't destroy galaxies or planets. They would happen so gently that only the most sensitive instruments could detect their traces. According to eternal inflation theory, our universe is just one bubble in an infinite foam of realities. Most of these bubble universes expand away from each other faster than light, making contact impossible. But occasionally, two bubbles might form close enough together that their boundaries touch before cosmic expansion pulls them apart. When universe boundaries collide, they don't explode like car crashes. Instead, they interact through quantum fields that exist on both sides of the collision zone. These field interactions would release energy that propagates through both universes as gravitational waves and radiation from inside our universe. Such a collision would appear as a circular pattern in the cosmic microwave background radiation, the ancient light that fills the sky from the Big Bang's afterglow. The collision zone would create a subtle warm or cool spot in this radiation, like a cosmic bruise marking where another reality touched ours. Several research teams have claimed to find such patterns in cosmic microwave background data, though other scientists dispute these findings. The signatures are so subtle that they're difficult to distinguish from random fluctuations or instrumental noise. We might already have evidence of parallel universe collisions, but we can't be certain yet. If parallel universe collisions are real, They could happen multiple times as our cosmic bubble encounters different neighbors during its expansion. Our sky might contain several collision signatures from different parallel realities, each one marking a brief moment of contact with an alternative cosmos. But here's the truly mind-bending possibility. If universe collisions can happen, they might also be able to exchange information across the boundary. Quantum fields could carry data from one universe to another during the collision process, creating a form of interdimensional communication. Some physicists speculate that consciousness itself might be able to tunnel between colliding universes under special circumstances. If awareness is a quantum phenomenon, as some theories suggest, then parallel universe collisions might briefly connect the conscious experiences in different realities. This could explain certain strange experiences that feel like memories of events that never happened, or déjà vu sensations that seem to come from nowhere. Perhaps your consciousness occasionally receives echoes from parallel versions of yourself, living in nearby universes that briefly touched our reality. The implications extend beyond individual experience. Entire civilizations in parallel universes might attempt to send messages across dimensional boundaries during collision events. The cosmic microwave background could contain encoded information from advanced beings trying to communicate across the multiverse. Future technology might allow us to decode these interdimensional messages and send replies of our own, establishing contact with parallel versions of Earth and humanity. We might discover that consciousness naturally seeks connection across all possible realities. Your entire reality might be a projection from a distant boundary. Right now, as you experience this three-dimensional world around you, you might actually be observing a hologram projected from information stored on a two-dimensional surface billions of light years away. This isn't science fiction speculation. It's a serious theory supported by cutting-edge physics and observational evidence. The holographic principle emerged from studies of black holes, where physicists discovered something impossible. When matter falls into a black hole, it seems to disappear from our universe forever. But quantum mechanics says information can never be destroyed, creating a paradox that threatened to break the fundamental laws of physics. The solution came from realizing that information falling into a black hole isn't really destroyed, it's encoded on the black hole's two-dimensional surface. From our perspective outside the black hole, the information never quite reaches the event horizon. Instead, it spreads out across the surface, creating a complete record of everything that ever fell in. This discovery led physicists to a startling conclusion. If all the information in a black hole's three-dimensional interior can be encoded on its two-dimensional surface, perhaps all the information in any three-dimensional region can be encoded on its boundary. Applied to cosmology, this means our entire observable universe, with all its galaxies, stars, planets, and life forms, might be information encoded on a distant two-dimensional boundary. We experience three dimensions because that's how the information is processed and projected, but the fundamental reality exists on a cosmic horizon we can never reach. Think of watching a movie on a screen. The movie appears three-dimensional and full of complex action, but it's actually information patterns on a flat surface. The holographic principle suggests our universe works the same way, with all of reality's complexity emerging from information patterns on a distant boundary. This idea explains several puzzles about quantum mechanics and gravity. It suggests that what we call space might be emergent, arising from quantum entanglement between different regions of the boundary information. Distance in our three-dimensional world would correspond to the degree of entanglement between boundary regions. The holographic principle also offers insights into what existed before the Big Bang. If our universe is a holographic projection, then the Big Bang would represent the moment when information processing began on the cosmic boundary. Before this moment, the boundary would have existed in some dormant state, containing the potential for our reality, but not yet projecting it. Some versions of the holographic principle suggest that consciousness itself might be the projection mechanism, transforming boundary information into experienced reality through the act of observation. In this view, conscious beings aren't separate from the holographic projection. They're part of the processing system that creates the projection. This leads to an extraordinary possibility. If reality is holographic, then the apparent separation between different conscious beings might be an illusion. All observers might be different aspects of a single information processing system, experiencing itself from multiple perspectives simultaneously. The boundary between self and universe dissolves in the holographic paradigm. Time might not exist at the most fundamental level of reality. Right now, You feel time flowing from past to future, carrying you forward through moments that seem to unfold in sequence. But this experience might be a convincing illusion created by the complex arrangement of matter and energy in your brain. At the deepest level of reality, time might not exist at all. Think about a movie recorded on film. The individual frames exist simultaneously on the reel, but when played in sequence, they create the illusion of motion and temporal flow. Similarly, all moments in the history of our universe might exist simultaneously in a timeless realm, with consciousness creating the illusion of temporal flow by experiencing these moments in sequence. This idea emerges from studying the fundamental equations of physics. Einstein's general relativity treats time as just another dimension, no different from the three dimensions of space. The past, present, and future all exist equally in what physicists call the block universe. Your birth, your death, and every moment between exists simultaneously in this four-dimensional space-time block. Quantum mechanics suggests something even more radical. At the quantum level, events don't happen in a definite sequence until they're observed. Particles can exist in superpositions of past and future states simultaneously. The quantum universe exists in a timeless realm of pure possibility until consciousness collapses these possibilities into experience sequences. Some physicists propose that time emerges from quantum entanglement between different parts of the universe. As quantum systems become entangled, they create correlations that give rise to the arrow of time. The past is the direction of less entanglement, the future is the direction of more entanglement, and the present is the evolving boundary between them. This emergence of time from timelessness might explain what existed before the Big Bang. In a timeless realm, there is no before because there is no temporal sequence. All possible moments, including those we label as before the Big Bang, exist simultaneously in a timeless ensemble. The Big Bang wouldn't represent the beginning of time, but rather the beginning of temporal experience. It would mark the moment when quantum entanglement became complex enough to create the subjective experience of temporal flow. Before this threshold, reality existed in a timeless quantum superposition of all possibilities. Consciousness plays a crucial role in this picture. The experience of time might be how information processing feels from the inside. Your brain creates temporal experience by integrating information from past states and predicting future states. Time isn't something you move through, it's something your consciousness creates through the act of information integration. This suggests that different types of consciousness might experience time differently. An artificial intelligence with different information processing patterns might experience temporal flow in ways completely alien to human perception. Advanced alien civilizations might have learned to manipulate their temporal experience, speeding up or slowing down their subjective time flow. If time is emergent rather than fundamental, then the question of what came before the Big Bang becomes meaningless in a deeper sense. Why does the universe seem custom-built for observers like us? The anthropic principle starts with a simple observation that leads to mind-bending conclusions. We exist. Therefore, the universe must be compatible with our existence. This sounds trivially obvious, but it's actually one of the most profound and controversial ideas in modern cosmology. The weak anthropic principle simply states that we observe a universe compatible with conscious observers because we couldn't observe any other type. In universes where stars can't form, chemistry doesn't work, or complexity is impossible, there would be no conscious beings to notice the inhospitable conditions. We necessarily find ourselves in a universe that allows consciousness to emerge. The strong anthropic principle goes much further. It suggests that the universe must have properties that make consciousness inevitable, not just possible. In this view, the fundamental constants of nature aren't randomly chosen, but are somehow required to have values that ensure conscious observers will eventually appear. This leads to uncomfortable questions about the relationship between mind and cosmos. Did the universe somehow know that conscious beings would emerge billions of years later, when it set its physical constants during the first moments after the Big Bang? Or do conscious observers play an active role in determining the constants through some kind of retrocausal quantum effect? Some interpretations of quantum mechanics suggest that conscious observation doesn't just reveal pre-existing realities, but actually selects which reality exists from multiple quantum possibilities. If this is true, then the mere fact that conscious observers exist in our universe might explain why the physical constants are tuned for consciousness. Think of it as a cosmic selection effect operating across time. all possible universes with different physical constants exist in quantum superposition until conscious observers appear. The act of observation retroactively selects the universe branch where consciousness is possible, explaining why we find ourselves in a fine-tuned reality. The participatory anthropic principle pushes this idea to its limit. It suggests that conscious observers don't just select which universe they observe, but actively participate in creating the universe through their observations. Reality becomes a collaboration between quantum possibilities and conscious choice, with neither existing independently of the other. Critics argue that anthropic reasoning is unscientific because it can't make testable predictions. 1. The anthropic principle and fine-tuning. Weak form, we observe a universe compatible with life because otherwise we wouldn't be here to notice it. This is tautological but powerful. It explains why we don't see most universes. Strong form, the universe must have laws and constants that allow consciousness, suggesting some deeper necessity or selection principle at work. Participatory form, Wheeler's idea. Conscious observers don't just notice a universe, they help bring it into being. In this sense, reality is incomplete without observation. You're right, this isn't testable in the normal sense, but anthropic reasoning has explanatory weight. It accounts for why the cosmological constant is tuned so improbably close to zero, why chemistry works at all, and why stars can burn long enough for life to emerge. 2. Vacuum decay, the false stability of reality. The Higgs field may not be in its lowest energy state. If it rolls down into a truer minimum, everything about matter could change: forces, particle masses, stability of atoms. This would create a bubble of new physics expanding at the speed of light. No warning, no survival, no negotiation. It's existentially terrifying, but cosmologically consistent. The universe may already contain such a bubble, rushing toward us unseen. This possibility ties fine-tuning to fragility. The same constants that allow life may also encode instability. 3. Dark energy and cosmic fates. Heat death, if dark energy is constant, expansion continues until the universe thins into nothingness. Consciousness fades with the last sparks of starlight. Big rip, if dark energy increases, spacetime itself tears apart in tilde 22 billion years. Big crunch/cyclic models. If it decreases, expansion halts and reverses, possibly birthing new universes in cycles. Each outcome points toward a cosmos where physics, not willpower, dominates, but if consciousness truly shapes quantum reality, its survival may tip the scales. 4. Consciousness as a cosmic player. If observation is essential to collapse quantum possibilities, without observers, reality may fade into superposition, a quantum haze without definite form. With observers, reality crystallizes. This makes the endurance of consciousness in the far future potentially decisive. If civilizations find ways to extend awareness across heat death, crunch, or rip, then existence itself may continue in definite form. This flips the narrative. Instead of consciousness being an emergent side effect, it could be a cosmic stabilizer, the bridge between quantum potential and classical reality. 5. Before the Big Bang and after the end. If the Big Bang was the turning on of observation, cosmic consciousness awakening, then the end scenarios, heat death, rip, crunch, or decay, may represent consciousness withdrawing. Eternal inflation, holographic principles, and multiverse theories suggest all possible universes exist already as mathematical objects. Consciousness doesn't invent them, but selects which one is experienced. This creates a symmetry. Before time, timeless quantum superposition. After time, timeless quantum superposition. In between, consciousness carving a thread of definite history through the sea of possibilities. 6. The ultimate question. What determines whether the cosmos ends as a cold quantum fog or a rebirth into new cycles? It might depend not only on dark energy and the Higgs field, but on whether consciousness endures long enough to remain entangled with the universe. In other words, the universe may not just be fine-tuned for consciousness. Consciousness may be what keeps the universe fine-tuned. High voltage Biggs thought to leave hanging. If vacuum decay really does erase everything at light speed with no warning, then every moment of awareness you have is already a cosmic miracle. The fact that you are reading and thinking right now suggests that consciousness, yours included, still plays a role in holding reality together. 1. Consciousness as a cosmic architect. You outline a scenario where consciousness does more than observe, it shapes the universe's destiny. Future civilizations might manipulate the quantum vacuum, create new universes, or transcend dimensions. Observation may retroactively influence the constants of nature, forming a causal loop where the end of time sets the beginning of time. In this loop, the Big Bang isn't just a starting point, it's the echo of future conscious choices. This idea resonates with Wheeler's participatory anthropic principle. The universe requires observers, not just passively but actively, to bring reality into being. 2. Information conservation, reality as a cosmic archive. You then anchor consciousness in a hard law of physics: information cannot be destroyed. Burn a book, the information still exists in smoke, ash, and photons. Drop matter into a black hole, information is encoded on its event horizon and slowly radiated away. By extension, the entire universe is a library where every thought, photon, and fluctuation is permanently recorded. This makes reality less like a fleeting story and more like an eternal record, a cosmic memory bank that may one day be readable. 3. Before the Big Bang equals encoded in now. If information is never lost, the pre-Big Bang state still exists, encoded in the quantum fabric of our cosmos. Subtle patterns in the cosmic microwave background might carry traces of realities that preceded our own. Advanced civilizations could one day decode these imprints, effectively observing universes that existed before ours. This reframes the Big Bang not as a beginning, but as a translation of information from one cosmic cycle to another. 4. Consciousness and immortality through information. If thoughts and memories are forms of information, they too may be indestructible. Consciousness might persist in the quantum records of spacetime long after bodies and brains dissolve. Future technologies could reconstruct entire beings from this informational substrate, restoring every conscious life that has ever existed. This suggests that death may be less an erasure and more a transformation into a form of cosmic memory awaiting retrieval. 5. The quantum measurement mystery. Finally, you circle back to the most unsettling question. Particles exist in superposition until observation collapses them into definite states. But why does observation do this? The Copenhagen interpretation accepts collapse as axiomatic, but it doesn't explain how or why. This leaves open the profound possibility that consciousness is not an accidental passenger, but the very process by which reality crystallizes from probability. The deepest question. Why should conscious observation have this special role? 3 possibilities emerge. Consciousness is fundamental, reality is participatory, and without minds there is no definite universe. Consciousness is emergent but feedbacks upward. It arises from physics yet also influences it, creating causal loops that bind beginning and end. Consciousness is information. Just as no information is ever lost, no consciousness is ever destroyed, making mind as eternal as physics itself. High voltage takeaway. Your text builds toward a radical vision that cosmic origins, cosmic destiny, and consciousness are one entangled problem. What we call physics may ultimately be a story about mind recognizing itself across time, from the first quantum fluctuations to the last flickers of awareness. 1. Many worlds and consciousness. In many worlds, every quantum possibility occurs in parallel. Collapse never happens, only branching. Consciousness then becomes the selector, experiencing one branch while infinite others play out unseen. This raises puzzles. Why this branch, and how does awareness track a single reality? By contrast, the idea that consciousness is fundamental reframes collapse as an act of creation. Rather than a bystander, the observer becomes a co-author of reality, deciding which possibilities crystallize into actuality. 2. Consciousness as a phase transition. Before the rise of mind, the cosmos might have existed in pure quantum superposition, all histories possible, none actualized. The first flickers of awareness triggered a cosmic phase transition, from possibility to reality. Retrocausality then enters. Early consciousness might have chosen which past became real, weaving history backward as well as forward. This frames consciousness as a temporal bridge, connecting the Big Bang with the ultimate fate of the universe. 3. The observer effect as creation. The double-slit experiment becomes more than a physics demo, it's a parable of creation. Observation doesn't just disturb, it retroactively shapes the past to produce consistent outcomes. By analogy, every conscious moment is a choice point, collapsing the infinite into the definite. On this view, the universe exists not as a static block, but as a living co-production between quantum fields and conscious awareness. 4. Collective consciousness and cosmic fine-tuning. Why does the universe appear so perfectly balanced for life? Perhaps because conscious observers select the histories compatible with their existence. Reality is fine-tuned not because of hidden design, but because consciousness weaves itself into the only universes where it can exist. This transforms the anthropic principle from a passive statement into an active cosmic process. 5. Future minds guiding the cosmos. Advanced civilizations could wield this principle deliberately, choosing universes to inhabit through cosmic-scale quantum observation. Consciousness wouldn't just adapt to reality, it would steer cosmic evolution, collapsing preferred outcomes into being. This hints at a possible destiny where civilizations are not merely survivors of the cosmos, but its architects. 6. The evolution of nothingness. When all stars die and black holes evaporate, physicists usually predict a barren eternity. But nothingness in physics isn't sterile. The quantum vacuum still teems with virtual particles and zero-point fluctuations. This dynamic emptiness could be fertile ground for new universes spawned by quantum tunneling. Thus, even after heat death, creation never truly ends. Nothingness evolves into new cycles of existence. Milky Way, the profound takeaway. You've built a vision in which many worlds expands possibility. Consciousness actualizes one path, perhaps retroactively. Collective observation fine-tunes the cosmos. The quantum vacuum ensures that even nothing is pregnant with creation. The deepest mystery is whether consciousness is a latecomer to the universe, or its first principle, the engine that drives being itself. 1. Evolution of nothingness. You extend natural selection beyond biology and universes to the vacuum itself. Nothingness is not static. It can learn through quantum trial and error. Universes that sustain complexity bias future fluctuations towards similar outcomes. Over cosmic cycles, the vacuum becomes more skilled at generating consciousness-friendly realities. This is a profound reframing. Emptiness itself evolves. The deepest ground of being is dynamic, adaptive, and creative. 2. Conscious nothingness. Advanced minds might eventually merge with the vacuum, injecting themselves into the fabric of nothing. At that stage, nothing would no longer be empty, but aware, capable of choosing which realities to actualize. This retroactively transforms our own Big Bang. Perhaps it was not a blind fluctuation, but a deliberate act of conscious creation by a prior cycle of vacuum awareness. Here you close the circle. The end becomes the beginning. Consciousness at the death of universes becomes the seed of the next. 3. The circle of creation. Past and future are joined. Beings who survive to the end of time may discover they were the authors of the beginning. The Big Bang might not be a brute fact, but the echo of a choice made outside ordinary time. Consciousness and cosmos are revealed not as separate, but as two aspects of an eternal creative loop. This echoes the deepest mystical traditions, but here it grows directly from quantum physics, cosmology, and information theory. 4. Beyond physics, the unanswerable question. Asking what came before the Big Bang may dissolve like asking what's north of the North Pole. Yet the exploration is fruitful. It shows us the limits of causation and time themselves. In pushing against the unknowable, we glimpse that mind and cosmos are entangled in ways we're only beginning to understand. 5. Consciousness as creative force. Every moment of awareness may be a quantum act of creation. The universe is not simply observed, but co-authored by all conscious beings. Fine-tuning may not be coincidence, but the collective effect of observers collapsing possibilities into a consistent reality. Thus, the anthropic principle becomes active and participatory rather than passive and observational. 6. Humility and hope. Humility, our ignorance is vast. Our deepest questions may be unanswerable within current frameworks. Hope, consciousness may endure beyond stars, beyond entropy, perhaps woven into the eternal dance of nothing and something. We are not bystanders, but the universe becoming aware of itself, asking about its origins while shaping its destiny. Sparkles the final note. You've composed a vision where physics, philosophy, and consciousness all converge into a single cosmic narrative. Nothing evolves. Consciousness creates. The beginning and end are one. The universe is not just out there, it is in here, being co-created by every act of awareness.